Hello and welcome to the Daily Space for today, December 5th, 2019. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. This week, a new research paper based on Sloan Digital Sky Survey data has brought us the kind of result that left me proclaiming, finally. This was one of those results that actually confirmed that one of the stories we've been telling about our solar system is actually true. This is the story about what will happen to our own Earth when the sun dies. The story that we've been telling is our sun will blow up into a red dwarf, and due to mass loss, it will slowly allow the Earth to drift away as both its gravitational pull lessens and angular momentum is lost. Now, one of the things about telling this story is we haven't actually, until now, seen other systems out there that have planets left around dead white dwarf stars, and a dead white dwarf is exactly what's going to become of our star, the sun. Well, that's finally changed. A group of astronomers led by Boris Gainsuk have discovered that the white dwarf star G29-38 is surrounded by a disk of hydrogen, oxygen, and sulfur that is consistent with the presence of a Neptune-like ice giant that's in the process of being completely destroyed by that white dwarf. With our own solar system, we always wonder, how will our sun survive? And not our sun, our Earth survive. And now that we know, well, yeah, other solar systems have this story that we've been telling, we have to ask, well, are the details of that story still correct? And it turns out in the details, things might not be quite so good for our planet Earth. One of our planet's great hopes is that our planet will migrate away from the sun. And in G29-38, we see not a white dwarf, we see a Neptune-like ice giant that has actually migrated inward. At some point, this planet, after the star was a red giant, migrated in so that it is now on an orbit that would have placed it inside the radius of the red giant phase of this star. So somehow, as the star dies, planets can fall inwards, which means it may still be possible for that white dwarf that our sun will become to eat up our planet, even if it survives the red giant phase. Now, depending on how you like your death, this may be a good thing, because that at least is a quick death to a world. And what this Neptune-like ice giant is experiencing is not a quick death. Instead, the ionizing radiation from this 38,000 degrees Celsius star is blasting the atmosphere off of the Neptune-like planet and dredging up deeper and deeper layers of material as it evaporates this planet away. Now, luckily, this is how we found the planet. A disk of former planet, shredded planet, a cloud of what had been the planet, is now strewn around this white dwarf star. And that material shows up in the spectra of the white dwarf as that cloud of material absorbs out the white dwarf's light. Now, in addition to just being like, hey, yes, planets do survive the planetary nebula phase of a star, this also indicates another way that we can go looking for solar systems like this. We can find them by looking for these anomalous materials around white dwarfs. So overall, this is a yay, we had the right basic idea, a ooh, we can still die, and neat, now we know how to find more worlds like this. I think that's overall good in the grand scheme of science for the good or for the evil. Now, in general, stars like our sun are considered to be fairly average. They're not too big, they're not too small. And they don't do anything too amazingly dramatic. They die as planetary nebulae, just exhaling their atmosphere and sit there as white dwarfs later. We generally pay a lot more attention to massive stars, things that will eventually go boom as supernova and form neutron stars and black holes in their wake. But it turns out that stars like our sun aren't nearly as boring and nondescript as we had thought. In a suite of 4 papers published in the journal Nature, the Parker Solar Probe publishes its first science results. And what they're finding is our sun is much more complicated than we thought. And we'd thought it was pretty complicated. In looking at the solar wind coming off the surface of the sun, this probe found that wind is being dragged by the sun's magnetic field and is carrying a whole lot more angular momentum. It's rotating a lot more than had previously been thought. And this has 2 major consequences. In the immediate future, this means we need to change how we calculate whether or not a coronal mass ejection is actually going to impact the planet Earth or not. We now need to take into account all of this rotational motion that we didn't think was transferred to the coronal mass ejection. In the long term, this means that the solar wind is actually carrying away far more angular momentum than we had thought, and our sun's rotation is going to slow down in ways that we hadn't previously included in our models. That's all cool, but it doesn't end there. They additionally found that waves of activity in the magnetic field, Arvan waves that we've talked about in past episodes, are there. They're generally doing their thing, but just like in the ocean, there are rogue waves that are substantially more powerful than had previously been seen or anticipated. And when these rogue waves of magnetic activity flew over the spacecraft, or when the spacecraft flew through them, depending on your perspective, they found that the magnetic field's polarity radically switched. If Parker had a standard compass like we've all held in our hands, you would have been able to see the needle spinning around violently. And these waves have particles that are going at thousands of miles per second, which is kind of awesome and kind of terrifying. And awesome and terrifying together may just be the best way to describe our sun. These fields are going 300,000 miles per hour. Yeah, flipping the direction of the magnetic field and really fast particles all in one. So, yeah, our sun, at least in the corona, is really cool. Way more complex than we thought. And is going to need an additional good hard look, which hopefully we'll get as the Parker Solar Probe continues its deep elliptical orbit that dives it through the sun over and over in the coming years. Now, I have one image of this that I can share with you. It's not the most exciting image we've ever seen, but this is what it looks like when you're inside the solar corona. I don't think these dark spots are actual features. I think those are places where the detector got overrun, but the caption of this image didn't explain it. All right, moving on to our final story of the day. This is a story of a massive galaxy cluster. In this case, we're looking at the cluster of Bell 85. Now, galaxies in general come in a whole lot of different shapes and sizes that are driven by their environmental conditions, their merger history, where we have small systems building up, merging over time to form galaxies like our own. But there's one specific kind of galaxy that we only find in one place. And these are the giant ellipticals, sometimes referred to as lowercase c, capital D galaxies that appear in the very centers of galaxy clusters. These systems are superheated by the gravitational pull, by the extreme gas in their environment, gas that has in many cases been stripped out of other galaxies and fallen into this gravitational potential. And these massive systems are made up of, well, many, many destroyed galaxies. And in Abell 85, astronomers observing its central galaxy found that in the heart of that galaxy was a hollow, an area that appeared less dense than what we're used to seeing. And when they looked at it closely to see what the black hole in the center looked like, they found a massive black hole, what they're calling an ultra-massive black hole, with a mass 40 billion times the mass of the sun. This is the biggest galaxy we have found so far. And in finding it, it's at a distance about 700 million light years away from the Earth. It both matches what was expected. When you see a hollow like this in the center of the galaxy, it implies that something happened that both sucked material in and then blasted it outwards. If you have a massive black hole, it's going to form an accretion disk as material falls in to build it up in size. That accretion disk is going to heat up. It's going to have its own fusion processes, and the light from that accretion disk is going to push out the material in the center of the galaxy, hollowing out the galaxy. This is what we expected. But this is bigger than we expected, which means that somehow it was able to allow more material to fall in toward the center. It was able to allow more material to build up that supermassive black hole without shutting off the process than we had expected. And it's unclear exactly how this happened. It could be through generations of influx. It could be that the way things fall in is different than we anticipated. There's a lot that we need to think about and learn. But for now, we have this cool new toy that we have to figure out what to do with in our computer models. And that's all the science I've got for today. So I will now take your questions, and I'd ask that when you type them in, you please precede them with that purple circle with a purple star in the center. While you type those in, I'm going to tell you that we are a product of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We are produced by Susie Murph, who will actually be here hosting tomorrow because I will be on an airplane on my way to Susie's house. Next week, things are going to be a little bit chaotic. The podcast will be going on no matter what. We're not quite sure how we're going to do the daily space. It may be airing at a very different hour. Susie, Annie, and I are going to be in Florida together, going on many grand adventures. Warning of chaos incoming, but the podcast will be fine. So go check out the podcast. That's all I've got. We are supported by you. I don't currently have our donation screen up. Let me fix that. Thank you for the bits. Thank you, an anonymous cheers. Thank you, anonymous human, for the 1,000 bits. I have a dog who's very interested in what just happened. Come on up. Do you want this? Do you want a cookie? Here, have a cookie. So we are in the process of doing our year-end fundraiser. This is going to be tied in with a 40-hour stream the weekend before Christmas. 40 hours hopefully allow us to finish bringing in $40,000. And this is the difference between what we are generally able to bring in through bits and subs and patronage and what we need in order to keep all of our programs going. So if you need a tax break, we are your tax break for those of you in the United States or living in other places where you can take advantage of a tax deduction from donating to a U.S. nonprofit. anything you could do to help would be greatly appreciated. This is how we keep our programs going. We have a variety of federal grants that are currently pending. It looks like the U.S. government may or may not have a budget by Christmas, and this affects how quickly we hear about grants. And the grants will only potentially fund our science programs. So if you want to see this show and all of our other programs continue, please see if your company can give, see if they can match your donations, see if there's anything, well, get the word out to others. You never know who might be willing to say, yes, I'm going to step forward and make sure that science communication continues to happen. All right, I hate fundraising. I'm done with that. I am now going to scroll back and see what things. Michael is typing the word perp. I'm very confused. Oh, he's trying to figure out how to do the purple star. Okay, I see your question. Could it be that some of the material fell into the supermassive black hole, was only a small black hole? That would be too dense to be blown away by the blast from the accretion disk. So I suspect this is something that either we don't understand the physics on in detail, or that happen over multiple epochs of time. A given accretion disk can only get so big before the light pressure that it emits is greater than the gravitational pull that it exerts on the material around it. And when there's this imbalance of light pushing more than gravity pulls, the accretion disk is able to clear the area around the black hole so that no new material can fall in. Now, if you have multiple epochs of this kind of activity, you can continue to build this black hole over time. But we generally didn't expect that this degree of this happening was a thing. So we need to go back to our theories and see what we can figure out about the details. Yes, Paranor is right. The Hangout-a-thon is 40 hours of very little sleep, but hopefully a whole lot of entertainment. Looking to see. I'm sorry that I can't give you a cookie to Paranor. I have one cookie left, and I just don't know how to pass it through the internet to you. So let's see. Still looking for questions. Scrolling. What galaxy is the most massive, Larry asks. I don't know. It definitely would be one of these central CD galaxies. I just don't know which one that we've found is currently considered to be the most massive. So Larry asks, in reference to coronal mass ejections, does that mean a coronal mass ejection can start at the far side of the sun and circle and hit us without warning? No. It just means that it's more of a curveball than anticipated. Our prior models considered that things didn't really carry the rotation of the sun. Once they were ejected, they were ejected. But it now looks like it's going to get rotated as it ejects, but only for a little while. The ejections are quite rapid, so they aren't getting too much influence from the magnetic field, but they're getting more influence than we'd been previously thought. This is more a matter of it looks like something that we thought was slightly going to miss us now could hit us, and something we thought could hit us is now going to slightly miss us. So it's a small deviation. Hanny asks, whoa, could the sun ever stop completely in comparison to the solar system? No. All of the conservation of angular momentum ties everything together. It's going to keep rotating. So PDR Aster NR1 raster, PD raster number 1 says the sun dies first or the Andromeda merge with the Milky Way. They're both going to happen about the same time, about 5 billion years from now. Which starts first, I think, depends on what you consider the start of our collision with the Andromeda galaxy. I think our galaxy and Andromeda will start to get deformation, slight changes in shape prior to our sun bloating up, but it's going to be close. Looking for more questions. Inside the radius of a star is not the place to be, Larry writes. I agree with you, Larry. I completely agree with you. I love the fact that Susie's like, this will look seamless on YouTube. Yes, yes, it will. Thank you all for your patience as I awkwardly started this show today. All right, that got me up to the beginning of this. Thank you all for being here. Rimble asks, how are things like the solstices calculated? How do you get the precise date and time? Is there an equation I could use in a computer program? Yes, it's just orbital mechanics. Yeah, it's just orbital mechanics. So the solstices are on the days when the south pole of the Earth is most pointed at the sun, and when the north pole of the Earth is most pointed at the sun. The year that your hemisphere is the time of the year that your hemisphere is most pointed at the sun is your summer. So as we go toward having the South Pole mostly pointed to the sun, here in the Northern Hemisphere, we're getting winter, while the Southern Hemisphere has summer. The Earth, more or less to short-term calculation use, maintains a constant pointing at the Polaris star. So what you want to look for is that point in the Earth's orbit when there is a straight line between the Earth, Sun, and Polaris, or between the Sun, Earth, and Polaris. And those are the 2 days of the solstice. Sloan, the Solar Dynamic Orbiter will be warning us of incoming coronal mass ejections, Larry. That is entirely true. And I think that is all of the questions we have for today. I'm now going to go finish cleaning up my munged together script that was interrupted by the launch of CRS-19 by SpaceX on its continuing cargo resupply mission to the International Space Station. CRS-19 will be docking with the ISS early Sunday morning, and we will not be bringing it to you because we will be sleeping. So thank you all so much for being here. Our next stream will be brought to you, I think, by Susie, unless there's another launch, I don't remember. And she will be bringing you the Daily Space tomorrow. We are so grateful that all of you are here. And we are a production of the Planetary Science Institute, working in collaboration with you. You are the ones who moderate us. You are the ones who help us find content. You are the ones who fund us. And for that, we are so very grateful. We are part of a 501c3. We are produced by Susie Murph And it takes a whole team to do everything that you see here. Myself, Annie Wilson, Susie Murph, we're just the ones who appear on camera. Behind the scenes, our instro and an entire group of amazing moderators are there helping us, well, with our instro, get our rocket facts straight, and with everyone else, making sure that this is a safe place for you all to be. Thank you, everyone out there, for making what we do possible. And wherever you are in the world, have a fabulous morning, evening, or afternoon. And I'll see you on the other side. Bye-bye.